everyone. My name's Daniel Murfet. I'm a mathematician at the University of Melbourne. My original field of research isn't machine learning. I'm an algebraic geometer by training, but these days I mostly think about theoretical aspects of AI, and in particular AI safety. I'm going to give an introduction to technical AI safety. As in Tiberio's talk, this will be largely grounded in the International Scientific Report. So I'll start with the risks that Tiberio already identified as listed in the report. So malicious use, malfunctions, and systemic risk. There are a wide variety of risks listed under these different headings, ranging from dual-use science to labor market risks to loss of control. There's also a number of cross-cutting risks, which compound each one of those individual risks. They include things like a lack of scientific understanding, which Tiberio already referred to. The question of whether or not safety testing is even a sort of justified paradigm in the first place. So this is one of the things I think we'll talk about in more length in the science session tomorrow, but it's not really clear that the safety testing that you do in other fields of safety engineering, where you do a limited number of tests and then hope to generalize to the behavior in general scenarios, is actually a legitimate thing to do for a generally intelligent system. So in many ways, we're just in a very unknown territory when it comes to assessing these risks and knowing what kind of mitigations are based on solid science. So what I'm going to do in this talk is attempt to draw out one of the sort of common underlying factors that shape how I think about each one of these risks. One of the common underlying factors of the technical and scientific aspects of these risks. As both Liam and Tiberio have mentioned, understanding and mitigating these risks requires an approach from many different disciplines. I'm just going to speak about what I think is one of the core technical and scientific underlying factors that sort of explains the way in which AI safety is perhaps qualitatively different from other kinds of things that we've understood and dealt with in the past as a technological civilization. So before doing that, I need to say a little bit about what kind of thing a frontier model is even, right? What kind of technical artifact is this? This is actually what Sonnet says if you ask, like, where did you come from? So it's not actually completely accurate, which is interesting, but it's more or less accurate. There's sort of a missing instruction tuning step there if you're familiar with this step. But the thing I want to emphasize right now is the sort of data collection part of this, the data collection and the pre-training steps in the production of these systems. So as you probably know, the initial kind of GPTs were trained on just sort of large internet text from sort of a automated scraping of the internet. These days we're using a large fraction of that, but frontier labs are, continually augmenting that with enormous sources of new, interesting sequences of tokens. So you collect a large data set. You then basically get a system to attempt to predict what the next token will be given a sequence of tokens in that large sort of training distribution. Then there's various stages where you do safety fine-tuning. You turn that prediction machine into something that's actually useful, into a chatbot or whatever else you want to do. Maybe it's a protein prediction model. You fine-tune, you shape it into something that follows instructions and follows certain kinds of guidelines on how to interact with people. Then you deploy it, and there's many stages after that. But the thing I want to focus on right now is that this is an industrial process, right? Deep learning started as an academic field. The very leftmost picture, and maybe leftmost two pictures in Tiberio's examples of image generation. It's no longer, well, of course there's a lot of academic work going on in deep learning still, but in terms of where the driver of progress is, it's most definitely in sort of industrial scale data centers necessary to manage enormous quantities of data and very large numbers of chips to do this pre-training. So this is an industrial process. It involves billions, tens of billions, maybe hundreds of billions of dollars of investment and ongoing sort of industrial processing. Okay, of course we have many other kinds of industrial processes like chemical factories, car factories. These are sort of processes where we understand each step, we go through the steps, maybe there's a lot of them, maybe they're not completely under control because although we understand chemistry, we don't have vision into what every single molecule is doing inside our large vats of chemicals. But nonetheless, we have some underlying scientific theory that sort of tells us within some parameters what's supposed to be happening during those industrial processes. In some ways, some important ways, deep learning and this industrial process on the previous slide is not like that. And that's sort of key, in my opinion, to some of the underlying risk factors from a technical and scientific point of view. So to explain the way in which this is not construction, let me dig a bit more into the second stage in the previous slide. So once you've collected the data and you've chosen an architecture for your deep learning model, those define some constraints. The constraint being that the deep learning model should be able to predict the next token given the previous tokens. Now that prediction isn't possible to do perfectly in all instances because any given sequence of tokens may have many continuations. So what the model is trying to do is to learn the distribution of next tokens given previous tokens. That's a constraint. It's a very difficult constraint, right? You might entertain yourself with the task of trying to actually perform the pre-training task for a large learning machine like ChatGPT or Llama and just sit down and take a text and see how well you do at predicting the next token and evaluate your perplexity and see how you do. It's extremely difficult. Many tokens are easy, right? Like many tokens, it's just some space or it's a common word like the or and. But many tokens are very difficult to predict. So these constraints are highly non-trivial. You need a large number of parameters within the network to even do a decent job of fitting to those constraints. And training is the process of iteratively modifying the network towards something that does as well as possible at satisfying those millions or billions, trillions of constraints. This process does not solve that problem. It doesn't produce a machine that actually perfectly models the data distribution. So it gets to some level of capability at solving all those constraints. And I'm doing this with my hand because there's more than one solution. At a given level of performance of one of these neural networks on this training distribution, there are many different ways of being that good at prediction. Okay, so this industrial process, unlike a chemical factory that has a series of equations that it's following and then it gets to a particular compound, this industrial process produces something, and more or less all you know about the something at the beginning is that it tried to solve the constraints and it achieved a certain level of being good at doing that. But you don't actually know the way in which it solves the constraints and how it's going to perform outside the setting in which you were training it. Okay, so the solution is not unique, and that's the way in which it's not construction, right? It's an industrial process, it produces something, but we know not so much about what that thing is. Moreover, maybe my explodey head goes on this rather than scaling laws. Scaling laws, extremely profound scientific fact, as Tiberio referred to. A second profound fact, which is maybe in some sense even less understood, even though scaling laws are also not very well understood. A second profound fact is that when you look inside these things that you just asked to solve these trillions of constraints, you see inside there something that resembles, perhaps, algorithms. So it's very clear that these are not simply memorizing the training data, although they do a lot of that, right? So many of you will be able to ask Claude, who is, and put in your own name, and it will give you a little mini bio. So it's memorized an enormous quantity of information from the training distribution, but it's not only doing that, and there's various ways in which we know for a fact that it's doing something like figuring out algorithms and then executing them on the data and context. And that's part of the emerging science of deep learning, is trying to understand what kind of objects these algorithms are, or even if that word is appropriate. Okay, so we have this industrial process. It produces something at the end. We don't really understand much about it. We look inside it and see there's interesting stuff going on. And fundamentally, it's a mystery. We know some things about it, and many people are working very hard to resolve this mystery, but fundamentally, it's a very nascent science. Yeah, well, we've already had the parables, so here's another one. Not the tortoise and the hare. So I want to talk you through a sort of, so that's the sort of brief picture of what these objects are as a scientific sort of phenomenon, these endpoints of trying to solve all these constraints. Now I want to connect that to AI safety and risks. Okay, so I'm going to talk through, I think it's 4 bullet points. Deep learning and large learning machines will be one example of a sort of scientific and technological phenomena that satisfies these 4 criteria. But I'm actually going to start by talking about another one, which is perhaps better understood scientifically. Okay, so here's something that could happen. A natural phenomena is discovered. It's not something that occurs every day. You don't see it outside without making a lot of effort to push the world into certain configurations that it doesn't otherwise naturally fall into. Making use of this phenomena requires pushing the world very hard. And when you do that, you create conditions which are extreme, very useful, but extreme. And by doing that, if those extreme conditions are not sort of within the range of tolerance of people, you create a condition of possible harm for people. What this means is that in such conditions, human safety requires control, somewhat obviously. Right? Moreover, the more you have to push the world to extreme conditions to achieve the useful outcomes that you investigated the natural phenomena to produce, the more you have to control the part of the world in which those conditions exist. And this is the obvious example, right? I mean, I know next to nothing about nuclear safety, so I did try and read this book. This is a diagram from this book. It's a lead-cooled fast reactor. This is the product of quite a lot of, as you know, scientific research and understanding. There's various gadgets over there on the right-hand side that you'll understand if you've studied thermodynamics as an undergraduate. There's nuclear phenomena going on inside there, of course. The natural phenomena in this case is nuclear fission. That doesn't happen naturally, usually. Like 1 billion years ago, there was apparently like a natural fission reactor going on somewhere, but that's not normal. To have a fission reaction, you need to push a part of the world into an extreme state. In this case, it's a physical state. It involves a high concentration of uranium, various other ingredients, and extreme temperature and pressure. And you do that in order to harvest that temperature, in order to create electricity and to do useful physical work. The result of all that pushing is that the inside of that reactor is not a place you want the little man there to be. So we keep him away, him or her. We build walls to keep those extreme conditions inside the reaction vessel. The larger the reactor, the more we're pushing nature away from its natural state, the more dangerous it is. Okay, and making all that work is the job of a nuclear safety engineer. Okay, so this is an example of this paradigm. The phenomena is fission. High radiation pressure and temperature are the extreme conditions that are involved in making that productive. And human safety engineering is, of course, a well understood discipline in this domain. I want to make the argument that building large learning machines like frontier AI models is in some respects analogous to this. Not completely, but there are genuine analogies to the situation. This is not a real textbook. That's one of my just starting PhD students, and Liam was a former master's student of mine. So, you've got like 2 to 3 years, so I guess that's long enough to write a textbook. So the extreme conditions in this case aren't really physical conditions, although data centers are rather extreme in some sense, right? Very strange configurations of silicon and other materials and large amounts of electricity. But that's not really the sense in which I think of the production of a large learning machine as being an extreme sort of manipulation of the natural environment. It's rather an information theoretic change. So the inside of a data center where you are producing one of these large models is extreme in an information theoretic sense. There's an extreme amount of data that goes into producing it, high bandwidth pipes for moving that data around, lots of matrix multiplications, etc. And the end result of that is a model which you can sort of make interact with other flows of information and get useful predictions. So in this case, the equivalent of the physical work that you get out of a nuclear power station is something like cognitive work. It's the work of making predictions. And those predictions are things you wouldn't easily get just by rolling dice. Okay, so that's the sense in which this is cognitive work, analogous to physical work with the power station. Okay, so the tokens are the sort of artifact that is the result of doing useful cognitive work in the world. All right, the question now is, what about this is unsafe? Right? Touching the hard drive with the weights for GPT-6 on it isn't going to like burn your hand. So what about this situation here is even potentially dangerous, right? How is predicting tokens supposed to hurt anyone? So I'll come back to this question, but I just want to make sure we're on the same page with the ingredients here first. So the natural phenomena involved is, well, there's an engineering aspect, but I would say the underlying natural phenomena are the scaling laws that Tiberio was referring to, the emergent algorithms that I mentioned, and just the basic observation that in some sense, like very disinflatingly for us, that intelligence actually seems to be pretty easy. I mean, I'm a mathematician, you know, this is like particularly disinflating for me. Using this requires pushing the part of the world far away from natural states. That's the large training runs and large inference clusters. There's a question mark there next to the sort of analogy for humans melt, right? And that's what I want to talk about in the rest of this talk. But for the moment, it's meant to be sort of unclear to what extent that's actually a sort of, those extreme conditions actually translate to potential harm for people. But supposing that, the job of mitigating that and keeping those containment vessels working is what AI safety would be about, right? Some part of AI safety. Okay. That's correct. There isn't anything intrinsically dangerous about a configuration of atoms that makes a rock, unless it has a lot of potential energy like it does at the top of a hill. And potential energy is the latent capacity to do physical work. Some physical work is very useful, but uncontrolled physical work, another word for that is ouch, right? So if that uncontrolled physical work, which is latent in that situation, is done on the person at the bottom of the hill, then they're in trouble. Well, there's an analogy here with cognitive work, right? So a large language model represents an extreme capacity to do cognitive work on the world. Not all forms of cognitive work, controlled or not, are naturally good for humans. So it's true that the weights of a frontier model are just a string of zeros and ones sitting on a hard drive somewhere. But that is in a formal sense analogous to the fact that the rock is just a configuration of atoms sitting somewhere. It's not really the point that ultimately it's just some configuration sitting on a hard drive. What is the relevant fact about that string of zeros and ones is that it represents a highly unlikely configuration of the world produced at enormous cost in money, resources, and human time. And you produced that situation in that part of the world in order to do work on the world. In this case, cognitive work. Okay, so that's how I would like you to think about these end results of this industrial process, the training process. It's an artifact that can do cognitive work on the world. And now I've reformulated this question from the previous slide about what is the potential for harm as a slightly more precise question, which is what is the potential for harm from cognitive work or uncontrolled cognitive work at large scale, speed, and scope. Okay, so let me now make this a bit more precise. So it's not really important there's a technical definition of cognitive work for this talk, but I'll just say that it's a change in the informational state of the world that wouldn't happen easily by chance. You wouldn't use ChatGPT, not in this room, but usually the rooms of this scale I'm talking to would be using it to do their homework. So you wouldn't use it to do your homework if it was just giving you random next tokens, right? So the cognitive work it's doing is a consequence of the fact that the outcomes it produces wouldn't happen easily by chance. The prospect of widely deployed human level or beyond artificial intelligence means that the action, it represents sort of tautologically the action on the world of an extreme amount of cognitive work at high speed, complexity, scale, and density. And by density, I mean just sort of embedded in everything around you, right? And so the way I think about the sort of underlying technical and scientific factor below or sort of common to a lot of the technical aspects of risks to do with advanced AI is that just like we have physical limits within which we're comfortable and safe, we also have cognitive limits within which we can handle our environment. And if there is widely deployed cognitive work of this kind, that may exceed those limits. So that's not safe by default. So we looked at a few examples earlier on, and I'll just run through a few and fit them into the kind of framework of what I'm discussing. So the cognitive work involved in this first example is the production of the text that the bots are using to manipulate you. But it's also, in some sense, indirectly doing, via that text, doing cognitive work on the information in here, right? Shifting the state of your mind in a direction it wouldn't have otherwise taken. So that's cognitive work. In the second example, we do cognitive work on the world to arrange it in a way that is beneficial for us. If there are other things in the world doing much more cognitive work, it's not automatic that we get the outcomes we want. If there are other things that are optimizing the state of the world much more quickly and with much more capacity than we are. And that's where ideas like scalable oversight, which is one of the technical research areas I'll talk about tomorrow, come into the picture. One disanalogy between cognitive work and physical work is that cognitive work can direct itself, right? And that's the capacity for autonomous agents, highly capable, acting out in the world, and the necessity to have scalable oversight over such processes. And this is where something like uncontrolled cognitive work. Of course, I'm talking about cognitive work, but we all understand that the current phase where tokens are things that we see on a screen is an extremely temporary state of affairs. And the guy who sits atop that rapidly rising green curve on Tiberio's slide, Jensen Huang, the CEO of NVIDIA, as he's pointing out here, right, we're seeing the translation of these tokens from the digital world into the physical world. So a lot of physical work will be downstream of this cognitive work that comes out of, I didn't need two of those. Okay, so to summarize, large learning machines represent a new kind of power in the world, power to exert large quantities of cognitive work on the environment at speeds and scales that aren't really possible without artificial intelligence. That, of course, has tremendous possible benefits, just like power plants are of tremendous benefit. But that benefit is derived in some fundamental scientific sense by pushing the world, some part of the world, into an extreme condition, physical or information theoretic. And human safety isn't compatible necessarily with being directly exposed to those extreme conditions. So that brings us to technical AI safety. This is not a term with a very clear definition. I'm not going to claim that this is the consensus definition and that it's truly canonical. This is how I think about it. So technical AI safety aims to provide scientific knowledge and tools, such as engineering tools, that help to protect humans from the negative effects of cognitive work that current and future AI systems will do on the world. Keeping in mind, as I was saying earlier, that this represents a kind of potentially new state of the world with a lot of cognitive work being done at high speed and large scale, and probably not inside some nice contained area, right? It's out there and among us doing this work. I also want to emphasize that while I do take very seriously risks that involve independently acting autonomous agents having goals or having emergent goals that they pursue at the cost of our safety and our values being represented in the world, that isn't a prerequisite for taking seriously things like loss of control. All right, so tomorrow what I'm going to do, there's one of the parallel sessions, the first session in the morning, I believe, is to dig into specific risks identified in the International Scientific Report, and I'll go through some of the research agendas within technical AI safety. But for right now, I'm going to stop, so thank you.